and today she's going to talk about automated searches for strong gravitational searches for gravitational lenses. Take it away, Jimena. Go ahead, whenever you're ready.
Thank you. Okay, so I'm mostly going to focus my talk on techniques that have been applied or that have been developed to DS and that can be used to find better lens transients in LSST. So the main three ideas that we have gotten from previous talks is that first, a time delay can be used as an independent probe to measure the Hubble constant to a very small uncertainty. Second, we're expecting that the number of lens transients will increase a lot with LSST. And third, that the main challenge with lens transients is that we need to detect them as soon as possible so that we can determine their time delay and we can make follow-up observations. So the question will be, what can we do with catalogs that already exist like DES so we can improve the detections in LSST? So this is kind of like an overview of a little bit of my talk. So for example, in DES, they're looking for looking at analysis of lens quasars, which I'm not going to talk about today. And there is also a search for lens supernova, which was developed by Rob Morgan, and I wanted to emphasize that work. And also we're going to talk about the methodology of finding lens transients by using catalogs of strong lenses to a watch list so that they can be prioritized. Okay, so first I'm going to talk about the technique developed by Rob Morgan to find lens supernovae. So what he did is that he developed a model, a deep learning model that is multi-branch. So what that means is that you can see that on one side of the model, it receives the image, and the image is analyzed by convolutional neural networks, which is a very common way of doing this. And then on the other branch, you see that this is our light curves. So these are analyzed by long short-term memory neurons. And what they do is that they find patterns across time in time series data, while convolutional neural networks find like shapes or patterns in the images. And then when you go to the deeper size of the branches, they get a fully connected layer. And then what he does is that he literally zips together the two outputs of the branches, and this is what you get here at the end, and then at the end, it makes a classification. So it is very interesting that that this technique uses both time analysis and image analysis. So he did this for a problem for classification in which there are, the groups are no lens at all, so galaxies, stars. Then when there is static lenses, and then when there is lens supernovae, that it's type 1a, and the other category is core collapse. So what you're seeing on the on the right, is it shows the performance of this model. So you can see that it performs the worst, for example, for DES wide, and then it performs the best for LSST wide, and we're going to see why. So he does simulations in which he takes into account the different camera parameters for the different data sets. So when we compare DSY with with LSST, we can see that the first very, very strong difference is the cadence. So the cadence is much higher for LSST. And then another way to test the performance of a model is to look at the confusion matrix. So here are the 4 categories that he used. And then if all the diagonal is full, then that will be that the model is perfect. So if we compare DS deep with LSST wide, you can see that there is a lot of confusion between the classes of core collapse and type 1a. And then between these two, and LSST is much better by a lot. And then that's because the scene for LSST it's much better than for the deep survey. Okay, and then what you're seeing on the right, so when he developed this technique, he also wanted to take into account to be used for alert brokers so that this method will detect lens supernovae as soon as possible. So this plot is kind of like quantifying that, in which you see here the number of epochs in the first detection. So the first detection is defined as a 24 magnitude, 24.4 magnitude in the R band. And you can see that from 0 to after 2 epochs, the true positive rate increases to almost 75%. And then as it goes until the 5 epoch, it increases to almost 90%. So it is, what this is showing is that this method can successfully find lens supernovae on real time. Okay, and then in this work, he applied this method to the DES deep survey. And after getting about 2,000 candidates, they were visually inspected, and 3 of them were selected. So these are the 3 final candidates. And right now, Jillian and I, Jillian is an undergrad, we're trying to work on finding models, lens models to describe the geometry of these systems. And I just want to say again, thanks to the organizers, because we have already been able to talk about this work this week. Okay, so then another method of identifying lens transients is by adding known static lenses to a watch list. And then when there is an alert that in an area there is a time difference in brightness, then you prioritize the areas where you know that there is a high gravitational field. So there are different kinds of searches. So for example, there are searches that are targeted. So they look at certain areas in the sky where they expect to see lenses. But now that we're getting now that we're getting more data, we should also start developing automatic searches techniques to find them as quickly as possible. So here I'm going to talk about my project in which I'm looking for these systems in DES, and I just wanted to mention that we also are looking for double source plane lenses, and as we are developing the architecture for this, we also want to find single systems. We also want to explore the idea that Simon asked yesterday, what if we have many lenses? Could we study dark energy with them? So that's an open question. And then another project is led by Eric Zaborowski, in which he's looking for these systems in Delft. So Delft is using the camera of DES, but it explores a bigger area. It is less deep, but there is more area that hasn't been explored before. Okay, so the goal of this project is to find strong gravitational lenses, static in DES, and then we want to use a deep learning algorithm, so we need to think about the training sample. So for the first step, we'll be creating simulations of lenses, and then we need to construct the negative sample, which should be as diverse as possible. And then we do the model training, and then lastly, we do the search in the whole data. So for the simulations, we use an idea that someone mentioned yesterday already, in which you use real images for the lens, and then we simulate the light of the sources. So what we do is that we overlap these 2 images, and this will be the complete simulation. So it is something really good of using real images, because they already have the realistic noise properties, and also they already have companions, as realistic images do. Then another thing to mention is that we use realistic colors for the sources, and they are drawn from a catalog of DES galaxies. And then the other thing is that we place the sources close to the caustics, which are the areas that allow high magnification, but not entirely on the caustic. Okay, so something that is extremely important in this kind of like automatic searches is that we define what is a discoverable lens. So we need to make sure that the lensing features are clear and are distinguishable. So to do this, we make cuts on different parameters. So they're just parameters that we define for the simulations to make sure that they are visible enough. So here I'm showing 3 plots in which they are not so good, and I wanted to show them because just to show an illustration of what are the parameters that we can control. So for example, we don't want sources with a low apparent magnitude, or we don't want images in which the source, the light of the source is too small compared to the light of the deflector. And then the same goes for the images. So we want images that are far away from the lens so they don't get blended, but at the same time we don't want images that are too far away from the cutout so that they are not in the cutout. Okay, and then now for the negative sample, we use a great variety of galaxies. So for example, for the deflector we use, as I previously shown, I use red magic galaxies because they are massive elliptical galaxies. And then we also use them here as in the training, in the negative sample. And then another thing that is important to add is possible false positives. So the normal false positives are usually galaxies that have bar features or spiral galaxies and mergers. The only challenge, let's say, that I have right now is that there are many galaxies present in my data set because there are many classic catalogs of this kind of galaxies. Then the other thing is a large variety of elliptical galaxies and round galaxies, and especially round galaxies sometimes are so smooth on the exterior that it looks like there could be a lens, but there is not a lens. Okay, and then something else are random galaxies. So these ones are galaxies that already went through the model and were cataloged as negative, and I looked at them very quickly, and they are all most of them are very small galaxies that are clearly not lenses. And then I also added images with artifacts because I found it easier to just get rid of those images. Okay, so now I'm going to talk a little bit about the model. I won't go into the details, but this model is based on transformers. It was developed by Google, and then transformers started being developed for natural language processing, and they hadn't been used for image processing because they are very computationally expensive. But then Google found a way to make them work. So the way they do it is that the first step when you put an image is that the image gets divided into 9 patches. And then, so this is the image divided into 9 patches. And then what it does is that to each patch, it assigns a position. So what is important is that the images are not randomly put in the transformer. Each one is assigned to a position in the image. So after this happens, they all enter the transformer. And then what is important is that they all enter the transformer exactly at the same time, so it's in parallel. And this is very different from convolutional neural networks because in the first step, the whole model is looking at the whole picture, which is something very different. So the main differences between this and, let's say, traditional convolutional neural networks is that this has a large field of view since the beginning. And in the other case, what happens is that with convolutional neural networks, you're focused on a very particular area of the picture, and it's only until deep layers that you see bigger features in the picture. So that's very different. And then something else is that it is very unfocused at first, and then something that people catalog as a disadvantage is that it needs a lot of data. But I honestly think that that's great. And then what you can do is that you can use models that are already pre-trained. So this is what I do. I use a model that is already pre-trained on random images, and then you can fine-tune this model to your particular problem. And then the motivation that I had for using this kind of model is that if you take, let's say, my simulations and you divide them into the 9 patches, you see that the position is very important. So the lens is always going to be centered in the picture. So the lens is always going to be in this patch. And then something else is that the arcs are always surrounding the lens. So if there is a lensing feature around here, it will always go like up. So this is the motivation of me to do this. Okay, and then this is the model performance. So the model is performing very well for the training set. And then okay, I will mention in the future how the search is going. So this is a confusion matrix, where you can see that the number of grown things is very small. And then I added some pictures to understand what is going on. So for example, in the false positives, you can see that there are still some galaxies that have arc features. Okay, and then this is a test on real candidates. And then here you can see that the model is identifying about 50%. And then what is cool about this sample is that it has the Einstein radius. So about 84% of them have an Einstein radius that it's outside of the cutout. So it makes sense that my model is not identifying them. And then this is another test on another set of candidates where you can see that it identifies many with a threshold of 50%. And then as the threshold goes down, which we will plan on using about at least 90%, this probability, the number of identified systems gets lowered, but I'm okay with that. What we care about is reducing the false positive rate. So we are expecting about 100,000 candidates, and I really want to lower the false positive rate because we're going to use visual inspection at some point, and I really want to value human time. So I really want to put work into this. And then these are some cool, interesting candidates that we have already found in DES. And just some key points from my talk. So Deep Zipper is really cool. I think it's ready to be applied to LSST. So as soon they start, think about Deep Zipper. And then strong lensing, even static strong lenses can be used to find lens transients. And my model of BAT is very close to being applied to the search in DES. So I'm very excited to see what I can find. Thank you.
Thanks so much, Jimena, for that lovely talk. Do we have any questions for her? We'll start over here with Nikki.
Thank you. That was a really great talk.
Thank you.
I was very excited to see the candidates that Deep Zipper came up with from the lens supernova candidates. So it's great to hear that you're also going to look into whether the lens model fits with them. Mm-hmm. Could you maybe share already a few results of that, or is that maybe too early?
So we right now we're trying to finding models that fit them. We haven't been successful yet, but I think one of the things that I wanted to do with this plot, was to show that it looks like it could be possible. We have noticed, after having this meeting, we have noticed that there are many things that we can improve in our modeling. Like, for example, it is possible that we think that there are 3 images, but maybe this one could be a galaxy, or there could be 2 images here. So there are many things that can still be improved in the modeling. But yeah, so far we haven't been successful.
Okay, thank you.
Other questions? Remy?
Thanks. Really awesome work. I think adding the false positive is a really long and really hard work, and so that's awesome that you're doing it. My question is, on the slide where you show that you don't want this kind of lenses because they're too small, this because they're not bright enough. Is your motivation here scientific? Is it because they're not exploitable, or is it to make your life easier on reducing the number of false positives?
Yeah, it's more about that, because if we're going to use visual inspection and humans don't recognize this as good candidates, we will get rid of them anyways. So it will be better for humans to not include them.
Do you have a sense, since you have made these simulations, do you have a sense for like the fraction of these, and in the end, how many strong lenses that means we are not going to monitor for transients?
Like if I have an idea of how many I could not find, no, I have no idea. Yeah, I don't know how to quantify that. Yeah, it's a hard thing to solve. We have thought about it a lot, but it's hard to provide a good answer.
Maybe I try to answer a bit provocatively. It's like every galaxy we look at is a lens. Photons lens behind. And so it's really up to us to decide of what sample we work with. And that is an investigation question, but it has to be propagated from the searches to your cosmology result. Yeah.
Other questions? Let me check if there are any on Zoom. I don't see any. I have a quick one.
Mm-hmm.
I wanted to ask, in the transformer model, so you segment the image into individual components. Is there any sense for interpretability? Can you get an idea for, if it identifies something as a lens, which piece of the segmented image it's using to make that classification?
So there is an area of understanding like how deep learning works, and I know that it's called like, I don't remember the name, but it has a name. I haven't looked into that, but it's something, so what I do for practical purposes is that I look at what is labeled right and what is labeled wrong. And even though it sounds silly, when you have so many simulations, you can quickly pick what the model thinks it's the strong lensing part.
Thanks. All right, let's give another round of applause for Jimena.
Thank you.
Next up,